好，我们开始上课。First review what we learned last week. Last week we learned how to complement three fields. Particularly focus on three scalar fields and discuss organization basically following the procedure for simple harmonic oscillators and eventually build up the field space, which we call the Fock space. For the free fields, the key message here is for each momentum, for each pulse, there is a simple harmonic oscillator. We use creation operator a dagger and creation operator a key to characterize the operators and actually give a complete definition, operator definition in fields I, and include stress y, x, e, in terms of function. Okay? By imposing the conservation condition, we can work out many commutators, operator relations for any very defined operator involved in three scalar fields. For example, California, momentum, or some other complicated operators. The message is whenever you can express your operator in terms of phi, you can decompose them in terms of A and A dagger. We're using the commutation relation between A and A dagger to work out everything, including the correlation functions. Okay? To discuss, yeah, that's the main content of last week. The last few minutes of last week's lecture, we mentioned propagator. So propagators is about the two-point function. We said not only one-point function, or some composite operator, even for 2 points insertions located at different points, we can work them out. We know how to express both of them in terms of A and B dagger. Again, just use the relation between A and A dagger to work out even for 2-point functions, which is basically the propagators. So the simplest one. So today we will continue to discuss the propagators. So the simplest one we mentioned last week is some propagator as follows. This is the simplest one you might imagine. You can say that this is nothing but we can give this as a two-state overlap of two-state. So sometimes this will call this a Weidman function. Just wait. We also mentioned the physical understanding picture of understanding by acting this local phi operator acting on the vacuum. So what does this describe? So we mentioned that it's not sharply localized some very function state. It says there is localized, but it's not quite sharp. Then eventually you can imagine that by doing this kind of overlap, you get non-zero results. In the quantum mechanics, for the X state shown here, so you can overlap, you get there. Now, in field theory, the local particle excitation is not like that sharp. You can imagine which even though that overlap is yeah, that's the property of this kind of simplest group of functions, propagators. Yeah. So the way to work out, I'm going to define those objects. Since we're using quite often later, let's define this kind of object. We use a notation E, and the variable will be x minus y, as mentioned last week, because the translation environments you use the function only x minus y. And we do a table. We'll give it here E, right? To work out this E function, it's straightforward. Simply observe. This is nothing but it's we plug in a dagger definition for both these five fields and plug into this definition, we eventually formula this. Our wonderful record. So we observe that both these are in this kind of dimension. So knowing this final result will be learned environment is very important. See you all the time. Because we know the final result. And it depends on x and y, the relation between x and y differs. And the that line, space line. And you just plug in some particular frame into this formula. Work on this. You get a result. Either you check this is not there. So both contact cases like this, both are not there. So I'm not going to repeat this regulation last week. I encourage you to check this yourself. And yeah, time case is not zero, it's quite simple. A little bit perhaps confusing to understood. It's the space line, even for space line, it's also non-zero. The reason I just mentioned is overlap of two general states. Okay? Whenever there is a non-trivial overlap, it will be non-zero. It doesn't mean a physical propagation from this point to that point. So this is what we learned in the last few minutes, last week's lecture. So instead, we will continue to talk about the propagator today. So another quantity, an important one, we can try to look at is the commutator. So commutator is include two keys. Okay? Two keys. Both keys is one, this one. First piece is x, y, second piece is x. As said, this is the same number. Since this is the same number, so it will be equal to average. Right? So two things will be equal, and in terms of this, we really can write this that d function dx minus y, dx minus y minus d to y minus x. Now we are going to look into in greater detail how to calculate this object, okay? Because this is very important. So how to compute this one? Let's write. Say, if I want to compute this object again by using this straightforward way, meaning that I plug in the AA diagram definition for both this phi and this phi, is plug into this formula, try to calculate. And what you get, not surprisingly, you get similar to that final integral structure, but carry two terms. The first term is the exponential minus IP dot x minus y. And the second term, there's a minus sign. The minus sign, right, is commutator to find the minus sign. The second term is the exponential IP dot x minus y. Notice this dot is a four-vector inner product. It's not a three, right? It's four vector. Which means it's not trivial, right? Because the integral is for the three-dimensional P. Okay? The inner product is four-dimensional. It's a four-vector inner product. So how to deal with this guy? Yeah, it's straightforward. But in order to make everything elegant, here we try to employ what we learned from complex analysis, contour integral. So the observation is this integral can be written in a particular form. For example, I can view this is nothing but, I just rewrite it, don't do much, okay? Don't do much. Just try to observe that this is nothing but, rewrite the definition for P0. Okay? This is nothing but P0, take the value at P0 equals to omega P, okay? Right? It's trivial, right? It's a definition. As mentioned many times before, this is a three-dimensional integral, but this is a four-dimensional vector, okay? In order to make the integral well defined, you have to specify, keep in mind, P0 is not an undetermined, or it's a dependent function, it's not. It's its value is determined by the omega P, okay? And omega P is determined by the spherical P, three-vector P squared, okay? Or plus n squared, which is nothing, okay? Right? So this is almost a definition. Just rewrite a little bit. Now there's a minus sign. I choose a plus. I shift this common prefactor inside to the second term. Then I will get minus 1 over minus 2 omega P exponential minus I P. And this, of course, the value will be P0 equals to minus omega P. Okay. It's just rewriting. Okay, I did nothing. I did nothing but just rewrite and make things more clear. See? Make things more clear. Now, if you do it this way, you immediately realize that this is the result. This can be viewed as a result that comes from contour integral. Right? Is that clear? Right? Remember what you learned in the complex analysis When you try to do contour integral, what do you do? Okay. In complex analysis, since you know the analytical function, right? A holomorphic function. If the integral, if the contour integral wraps some poles, okay, you can easily compute that contour integral. Pick up the residue. Familiar with that? Okay. Now we also learned not only that, actually the complex contour integral can help us to compute even some real integral, real axis integral, right? Right? For instance, if your integrand something you have to integrate if it carries a pole in the real axis. Okay? For those cases, it's very convenient to using contour integral. You just get around the pole and form a contour. Close the contour. Make sure what happens inside this contour. Right? Better to have a finite, simple, or not too much complicated poles. Then you can again by picking up the residue to compute the contour. Straightforward. Now. Here we need a little bit of observation or some tricks. So we just try to observe this final result and then try to write down what is the original contour integral. Okay? We should view this as a final result and try to write down the original contour integral for this result. Okay. Of course, the observation will be the contour integral, since clearly these two objects, these two values indicate that there should be two poles, right? You see? Because this looks like a calculated residue, right? I evaluated some formula, at some point for P0. Evaluate this guy, right? So this really looks like the residue of structure, and I try to recover or find the original contour integral. That integral must be associated with P0, right? See? Because the pole is associated for P0. Now these are real numbers, plus omega p and minus omega p. Then you can imagine, okay, if there is a contour integral, the contour integral should be associated, first of all, should be associated with p is a P0. P0. Now P0 possibly will have two poles. Okay, two poles. There's a pole here, another pole here. Okay. And the two values will be minus omega p and plus omega p. Clear? And the integral is about the integration along the real axis. Okay. Now, in order to have such kind of pole structure, the simplest integrand you might want to write down is nothing but what is the p squared minus m squared, right? The p squared minus m squared is the P0 squared minus p three-dimensional p squared minus m squared. By definition, this is omega p squared, right? So, you see, such kind of denominator will have two poles, plus minus omega p. See? So, then by that observation, just purely by observation, I can deduce this will be the right structure. Okay? This is the good structure for construct that. Okay? Now, what is the remaining structure? The remaining structure should be associated with this remaining part, right? Right? So a little bit of guess, it's not actually complicated. Then you realize that the integrand so looks like this way. Okay, and arrange the sign properly. Then you write down the integral, which is actually indeed P0 integral run over from minus infinity to plus infinity carry two poles. One is plus omega p, the other is minus omega p. Okay? And the times this factor. Okay? This factor is a little bit trivial. It's just the same with this function. Now take care of the signs. Okay? Compensated by minus sign. Then you can check. Indeed, if we want to go back to the second layer of the undervalue to try to calculate this contour integral, you know that for such kind of integral, you have to specify the contour, right? Otherwise, you have some ambiguity. It's not very defined, okay? Because once there are poles, you have to specify by which way you get around the poles, right? Meaning that you have to specify explicitly which contour you are doing your integral. Otherwise, there is ambiguity. Is that clear? Okay, so I just draw the contour by hand here. This, of course, this is not the unique choice, but this is the one choice. The point is you can check. By choosing this kind of contour, construct this integral, you can easily check yourself. You get nothing but the object in the bracket. The object in this bracket. Is that clear? This, to some extent, answered the question appeared last week. Someone asked why you don't express everything in terms of four-dimensional integral. You see, I did it. You see, I tried to equivalent the three-dimensional integral to a four-dimensional because I add up one-dimensional integral. You see, but the payment is you have to carefully insert the structure here, okay, in order to make these two values precisely the same. That's the way I did here. Now, of course, we don't want to forget about the other structure. So if we want to really make sure these two guys are equal, also maintain this three-dimensional integral. See, the integral becomes four-dimensional. Now, because my integrand carries the pole structure and specify the contour, the paths in this way, you can check that this is not enough. This is about complement. Okay? Let me stress it again. Only by writing down this integral is not enough. Okay? Associated with this choosing of contour will be equals to previous result. Okay? This is the second year undergraduate course exercise. Okay? If you are not familiar, or some of you are not familiar, I strongly suggest you go back to demonstrate contour integral. It's important. We're using it quite often. This course. Any question about this factor? Yes. Can you speak louder? Hmm? Okay. Oh, it's minus, right? This is a minus. Yeah, I have minus. That's the term. First term is this one. Second term is leave. But for the second line, you have to be very careful. Here I write a minus. Okay? Because here I take a value of p0 equals to minus 1. So the sign is correct. Any other questions? That's precisely the question. Okay, I didn't mention the, okay, why, okay, let me just mention why you can get from here. The logic is as follows, I mentioned, but let me be more precise. So you see, and then you keep asking, right? You should ask, why this particular choice of this kind of funny like an I is a contour, okay, that precisely give this result. Right? We can ask. Anybody else give an answer for this question? Yeah, the point is, this is related to whether x0 and y0, which one is bigger. Okay. Let's do analysis. So if x0 is greater than y0, then one can close the contour from below. Close the contour from below means I can do the close the contour from below. Okay, why from below? Why from below? Use this condition, right? Yeah. Because if x0 is bigger than y0, let's check a little bit for details. If x0 is greater than y0, this is a positive, okay? For the zero component, right? Right? Now, if the imaginary axis for the P0, okay? The imaginary part for P0 is the minus infinity, can make sure, okay? Make sure this factor is decayed, right? But from what you learned in the second year undergraduate course, only you can close the contour only provided the integrand better to decay at the far region. Then you can safely prove the associated contour integral theorem, meaning that you can simply just pick up the contribution from the residues. Don't worry about anything else. Okay? You see? Now, if the sign is opposite, then we can reproduce the bracket as said in this star. I mean, this is my star formula. Now, what if we have the different sign for x0 minus y0? Okay. In this case, of course, the same logic, you should close the contour from above. Okay. And what? In this case, because the poles are located at the rear axis, if I close that contour from above, what do I get? What do you get? No, it's not moving. Yes, zero, correct. You should get zero. Come on. Okay, that's your second year undergraduate course. If you learn it, you should not. If you do a contour integral, nothing happens inside the region. You should get zero, right? If the function is an analytic function, you should get zero, okay? So the integral is zero. This means what? To make it the precise equality between contour integral here and this formula, we have to put another condition, right? One more condition. The condition is this one. Okay, this one. I said the contour integral with that pole with the specified contour path could potentially produce the previous result. Now we carefully examine it. It's only true if x0 is greater than y0. Because if only in that case you can close the contour and wrap this pole. Okay, you see, If I lose one of the pole or both of them, I will not get a residue, you see? Because I want to get both two residues. There are two terms, right? The two terms in the first one. I would like to get this one, also this one, you see? It's coming from these two poles. Now by contour integral argument, in order to produce that two terms, you have to close the contour, right? Wrap inside, wrap included these poles, okay? But again, carefully justify the infinite behavior of this integrand function, okay? You realize that this is only possible if x0 is greater than 1,0. Not the opposite, okay? If this is the opposite, by the similar argument, we can close the contour from above, okay? In that case, we will get 0. Of course, 0 is not good. Then, which means you cannot reproduce the first line result, okay? And we want to precisely reproduce the first line result by a contour integral construction, okay? Two conditions, remember that? Okay, let me stress again, two conditions. One is specify that path in this way, okay? The other is x0 should be greater than 1,0. Both these two conditions are necessary. Now, by this kind of condition, then we successfully write down a contour integral here. And then can reproduce this one. Now, summarize or put everything together, this eventually means that we can define what? We can define this contour integral with this path. Okay? Let me denote it as star. We can define star as what? As another label, which is dr x minus y. This is defined as a theta function x0 minus y0. Let me first write down and then explain what does this actually mean. Okay. We can do the following, okay? Don't be confused. Now I claim, okay? I switch a little bit of my angle, my viewpoint. I try to treat this integral with such kind of particular contour as a new object I want to define or give later. Okay? My starting point is this result. We try to using contour integral to reproduce it, but now I switch a little bit. I think this new object looks very nice, right? It may be also very important. Now I try to give this whole object a definition. Yeah, that's my new viewpoint now. I want to define this package with this guy. I define this guy and give a name as dr. Okay, dr. I will explain what r means and why we have named it dr. By this moment, it's clear. If I want to define that one, that will be equal to a step function times the initial commutator correlator. You see? Is that clear? Because that's precisely matched, right? Because this function essentially means only when x0 is greater than y0 is equal to this guy. Otherwise, it's 0, right? That precisely match the contour, the integral result I just mentioned. Right there. Now, two objects. I don't confuse them. Including the initial one, three objects. Okay. Try to clarify them in your mind. Okay? This is the simplest one with the Riemann function. I want to go a little bit complicated higher level of commutator correlators. Okay. Now I want to get a little more fancy object. Okay. I attach it to a third different object. You see? I want to define another one, which is dr x minus y. Rx minus y has its own definition in terms of control integral with a particular class. Okay, clear? Now, if we want to build up the precise relation between all these different three objects, okay, you can write down the formula in this way. See? Clear? Which involves a step function. Here, this is important. This step function only for the variable is positive, then it's 1, right? Otherwise, it's 0. Right? This is the definition of step function. Okay? Now, as said, sorry, this may be equal. Sorry, as you can see this as a matter. As said, this is defined by a four-dimensional P interval with I P square minus M square times the exponential minus I P dot x minus y. Okay, with the again. Just write down this integral is not enough. Okay, you have to specify the path with the path or with the contour. With the contour star. Let me mention the star also can mean particular contour. Okay? With the contour, with a particular contour that I put there. Okay. Okay. Do you have any question about these three different propagators? Okay, and let me continue. So after knowing this one, try to push a little more the discussion get very interesting objects. Now, depending on taste, okay, you might think define the propagator in such a way, it's a more natural and elegant way. If you like a complex analysis, for instance, or if you like this four-dimensional momentum integral, okay? That's indeed, it's beautiful, you see, it's beautiful. This is amount, later we will see that it's amount to see some momentum space propagator, and you do some Fourier transformation. That's it. Okay. So in that sense, it's elegant. Yes. But as mentioned, the subtlety here is you have to specify the contour. Otherwise, it's not very defined. Okay. Because it has holes. Yeah. Now, by this kind of observation, you immediately realize that you can choose such kind of path or contour in this way. I can choose other different types. Okay. Right? If I take this kind of definition, it's more elementary. I can try to switch to some other contours and try to define some other propagators. Right? Just only this way. So clearly, the choice I made there of contour is not unique. Then, what if other contour? For example, I can choose the contour. Again, this is minus plus. Okay. See? This is another contour I choose, right? It just means for the left one, I move, I get it around from okay. For the second one, I do this. These are all very defined paths in your complex analysis. Not easy. Some of you may not agree with it. It's okay. It's simple. Just about the integral. Another something simple. It's constrained by all theorems. So I can specify the controller in a different way. Then it gives a different definition for my logic. Okay. So one can write the calculation if the controller I choose in this way, then I can write the corresponding correlation function. With this control, I use star here. Yeah, this is a control star. We can actually use another control. Yeah, this control. Then I denote this particular correlator as the EX1. I just changed the subscript from R here. Where's my? Yeah. I use an R, right, to specify this particular contour or particular correlate. I switch to another subscript F, X minus Y. Okay. You can imagine that this kind of definition will maintain everything else apart from the different choice of the contour, right? So basically, maintain all the other structures. I just copied the random from here, from the DR. I copied this one. Copy this one. Here, let's specify the contour is different. I define a new object, which is DS. Okay, X minus 1. Okay, clear? Now, if you see, okay, whenever I try to refer to a different propagator, I have to plot the two class controllers. You see, the homework, when I mentioned, I mean, this kind of propagator, I have to plot a different component. Conceptually, it's very simple. I mean, technically, you can write it every time. Write it every time. So in this case, since we will see later, this object is quite a physical object, okay? Quite a useful object. It's actually very important. And also elementary object for the finite vectors. So we want to employ some trick to simplify the notation. Just the notation. So what is the better notation? Better notation is you don't want to draw this particular contour, that's fine. The payment is you have to put an additional small piece, okay? Which is you have to plus I minus I epsilon. This is just equivalent thing. You add a little small piece I epsilon. What is epsilon? Epsilon is a small positive number, constant. Okay, it's not a big deal. It's a constant. It's equivalent to the don't do this unspecified control. Okay, the logic clear? I just try to use another way to do the same thing. I don't want to every time draw the contour. Okay, look, this is my choice of my contour. No, don't do that. It's too complicated, technically complicated. Now, I want to employ another trick. Just simply put a class I epsilon. Epsilon is a small positive number. Can anyone explain why these two choices are equivalent? Why? They are equivalent, right? Can you explain that? Why? What's the reason for this equivalence? Because as I said, we always take the definition of this small epsilon as a positive small constant number. Okay. Then clearly, this new function entirely have two different slightly shifted poles, right? The pole is not the original pole without an I epsilon. Yeah? The pole shifted a little bit. Now, how they are shifted, in which way, precisely consistently to the choice of such kind of control. What that means is, as I said, I can forget about this deformation, small deformation I have, so I can insist this is p squared minus m squared. Then you have a real code located on the real axis. Right? You have to specify, get around the code, you have to specify the control class. Okay? Now, I can, as said, I can choose another way to do the same thing, which is I don't specify some kind of shape or contour, but just add a plus IF2. That essentially plays a role to shift the original pole above the midpoint. Above means the distance is epsilon. So that epsilon is infinitesimal small. So it's just shift a little bit above. And this pole actually shift a little bit down. Okay. This is up, and this is down. It's solve it, by the way. It's not a new equation, just solve the equation. Take this equal to 0 with this IF. Justify yourself, you need this two poles that shift to right. Okay? Because of now the original two poles now are shifted a little bit, I don't need to deform my control. Just keep the original control enough, right? See? So it's a matter of you should shift your control a little bit, or you should shift your control. The point is, eventually, this is the only trick. Eventually, in the intermediate step, calculations will always carry this high up. But eventually, everything must go to 0. You finish all the calculations, including whole integration. So this I epsilon only plays the role to specify the particular. So, yeah. So by understanding that, you can forget about this part of the entire definition. We have to just write down. It's very fine. Of course, keep in mind that the common assumption, or everybody agrees, the common assumption is epsilon is small altitude constant will be set to variable in the end. Yeah. So sometimes some use here. I have this but it's a convenient trick, okay? Later you will see this is really a convenient trick, okay? Yeah, sometimes you just put a small epsilon term, you solve that, all the same, all the subtleties, okay? So this is a little magic trick, but it works in this way, in a very clear way. Now, you give a definition. I give a definition for this df. I have the df. I told you how to compute the df. So let's do it. I said df is important, but better to know how to compute it, right? So how to compute the df? Compute the df. As I said, since it's associated with the specified control is that particular choice. Okay. So to compute the df again, similar to this classification. Yeah, you have to discuss case by case. Okay. Because this kind of condition will allow you to close the contour in different way. Okay. So again, compute the. Now we want to compute the left. So when x is 0, y0 is greater than y0, instead one can close the control from below, right? Again, the main reason why this argument is true is that the moment the function integrate the function, it's better to decay in the boundary regime. Otherwise, the function blows up, or the integral doesn't make sense. Okay? Not use the residual theorem. Better to decay. This condition is precisely to make that function decay. So this corresponding from below, closing from below. From below means again you can do this way and do this. Another there is given by 0. Now in this case, now I can close the control in that way. Clearly, this kind of control will only include this one, right? See? Yeah? We only include the recipe coming from this pole, but not this one, right? You already get around this pole, okay? So in this case, df x minus y under the condition x0 greater than y0 will be equal to the residue contribution coming from the right-hand side poles, okay? Which is nothing but this term. So what is this? I read the support, but what is this? Because you remember, this is nothing but dx minus y. Okay? This is dx minus y without any index. Okay? Don't confuse yourself. I have written df is new of d is something first of but this point is only under this condition. Only in this condition, only under this condition, value goes to this one, which is not. Okay? Now, of course, you can imagine when x0 is less than y0, you can only close the control from above. Which essentially means the control interval. The control interval will receive the contribution from the first level. So then this will be equal to the contribution from the left. To check yourself, it's nothing but IP. Now, there's a sign difference. This is minus, this is plus. The sign difference is equivalent to the x multiplied by y minus x. See? So this is nothing but the e y minus x. There. Okay. Now, since I get such kind of message, it only matters if you switch the x multiplied to y minus x. I can write another elegant formula for df, right? Because this is closely related to d, okay? I can just express the df in terms of d itself. So summarize these two results. The real thing I can do is df of x minus y to, again, its usual step function. And the definition for because dx minus y is nothing but phi x phi y inserted in the vacuum two-point function. Okay? You see? Another step function, y0 minus x0 and vacuum phi y and x. Okay? I just rewrite these two results organized together. Okay? Because of these two results, see, D is nothing but phi, right? dxy is phi x phi y. dyx is phi y phi x. You see? These two results come out for individual dependent conditions, which is greater than 1 or less than 2. Okay? So I use a step function to organize the previous results for df and make a more elegant formula for df in this way. Okay? Now let's check a little bit or try to understand what does this mean. Okay? What does this mean? This means what? If you try to understand these two different terms in a uniform way, okay? What's the meaning of this kind of order or organization? You see? See, x0 is bigger than y0, then the phi x should be on the left. You see? On the left, you see? Now, if y0 is bigger than x0, then y is on the left. You see? Okay? This means something, right? There is some choice here, right? This means what? If you try to take from right to left as some kind of time direction, okay? Because x0 and y0 are time, right? It's a time of these two insertions or two operators, two phi operators, right? If I take my time direction from right to left, you see, then you can easily understand this order. It just means if you give me two operators, okay, depend on whose time is later, I always insert in the left. You see, this is my time direction. Okay? Okay? If the guy is earlier in the time direction, I always move it to the right. Yeah, that's what it means, right? See? The point is this kind of ordering works for all the general phi x and phi y. Okay? Okay? So for this reason, we define this kind of propagator or two-point function as time order. And I use a simple way to use this kind of object. Okay? I'm just using a T here. T operator here. T is a time order. You see, you check this. This actually equals to this. You see, equals to this, right? See? Yeah, because the step function essentially does the job to order in the correct way, in the time ordering way. The point is you should view this from right to left, the time direction. Okay. See. Now, more concretely, you see, you're starting from some ground state. Okay? Since your time direction is from right to left, starting from a given state, in this case, the vacuum state. Now I try to evolve, right? In general, I will try to evolve, right? Right? Now, at some time, you meet the phi x, and then you meet another operator, phi y. And then this is the physical way to understand what this kind of movement function describe, which kind of process. The point is using this abstract T operator or time ordering operator. This T is not a time reversal symmetry generator. Okay, it's totally different. It's just a time order. fancy T. It's not an operator. It's a fancy T. This is a time ordering operation. That's the handler. It only does the job to make the following operator in a time ordering way. That's it. Right? The point is, you see, by doing this one, you are free to switch. You are free to switch the whether this insertion is here or here, right? You see, doesn't matter because T guaranteed. The time ordering operator guaranteed all the earlier insertions should be located eventually at the right, okay? Okay, all the later ones should be located on the left, yeah, right? So it doesn't matter. So mean what? This is just equals to T phi X. It doesn't matter. I order the time in the correct way. Yeah, that's another notation. So you see, in today's course, we try to introduce many different notations, many different different lanes. We have to try to clarify the different objects. Okay. So then let me go back to few remarks. So why we choose F here? Okay. So F is denotes that this is actually there's another name for this object in Feynman propagator. It's a Feynman. Now go back to this one before I erase it. So why I choose an R here? R has also a particular meaning. R means retarded. R means retarded. See? Because it only have one contribution. It only have non-zero contribution. Only if it has non-zero contribution. Only if x0 is bigger than y0. See? No two pieces, only single piece. See? Right? So we call it retarded. But lame is a lame. If you don't quite fully understand, it's okay. This is his definition. It's just a lame. All the lames has some comes from some particular understanding. Now you are keep asking what other choice. We already made two choices. So let's have two choices. I raised that for retarded propagator. I also make the specific for Feynman propagator. In fact, you can have another one if you record the advanced. Advanced is the opposite meaning, has opposite meaning for retarded. Okay. Okay. So if you choose another different control, we can define another propagator. See, you may want to choose such kind of looks a little strange. It's actually equally very defined. If you want to choose a contour in this way, okay, then this gives you another propagator defined, which is the basis of the box. Yeah, but then maybe you see, okay, by combinatorials, I have both choice, right? The equation is great. I can do a both one. Both one is this is upper bound, and this is lower bound, right? Indeed, that propagator also is right. Usually we don't use it. Usually people forget. There is such kind of object. Sometimes we just ignore the EF tutor. Okay, it's quite close. So there are totally four physical propagators. The elegant way to organize this or define these four different propagators is really by the choice, particular choice over control. That's the key message here. Now, to summarize, we introduced the first Weidmann function because it's the simplest. Okay. We try to look at the commutator because we want to understand a little bit of causal relation, causality. Okay. Because we're yeah. So let me try to finish the causality discussion. And then later we said that we also raised the four different kinds of propagators. We see we have more physical ones. We will continue to discuss why they behave more physical. This is for the DS. Okay. So the commutator is defined to solve the causality problem. So why this is true? So the physical interpretation, this is about the probability. The physical interpretation of the commutators is given by to detect whether the measurement at one point can affect the measurement at another one. And in terms of formula, we already at least a pattern calculated this commutator to get some result, which we raised and realized that this is nothing but e x minus y minus e y minus x. Okay. So you can check. Now we want to finish the causality part discussion by looking the general results of also these commutators. Okay, also these commutators. So this is the result of this commutator. This commutator. This itself is equal to the mechanism value of the matter, which is the number. So this equals to this. Also, because of this is Lorentz invariant, as mentioned many times, because the final result of this guy is Lorentz invariant. Okay, is Lorentz invariant. So depends on its time-like x, y, or time-like or space-like. You can choose a particular frame you like. Okay. Right? Then we immediately realized that in last week's discussion, we actually already know the result. Because we already find the result for equal time commutators. You know that? Equal time is space line or time line? Or space line, right? It's equal time. So we already know the result for equal time commutators by quantization condition. Okay? By Lorentz invariant argument, we basically know the result. We know the result for this space line. So this means space-like, okay? So if the 2 points are space-like, Final result is also Lorentz invariant. We already know the result. The result is 0, right? Because this should be equal to the equal time commutator, right? Right. So that's a particular frame. I just choose a frame. The 2 points are standing at equal time. That's fine. Now, by a continuous Lorentz boost or Lorentz transformation, we can transform to whatever we want. Other space line. We have all Lorentz be transform related. And I know the final result is Lorentz invariant. It does not depend on which. I just choose the same. So we already know the result. I don't need to compute. Now, in the opposite, if these are time-like, we also, to some extent, we also know the result from last week, right? I know last week we tried to compute the time-like, one part of the time-like results, right? We get something like exponential minus IMT if t is very big. Remember that? Now, you have 2 pieces of that kind of integral, right? From last week's integral. Okay? The point is, either of them is not 0. So if you add up, they're also not 0. You don't cancel. So it's not 0. So in this case, it's not 0. So this means that this final result eventually means that the commutator is a good detector. The commutator is a good detector for the causality. Means that if the 2 points are space-like, whatever how much space-like structure, then it should always go to 0. Okay. Now, if it's not space-like, means if it's causally related, okay, then it's not 0. This essentially means this is a good detector for causality. Okay. We know causality. We understand the causality coming from the special relative, like structure. We have causal, some kind of a causal structure that we talk about whether 2 points. For instance, this is my cone, and I always choose one of my points. For instance, the origin is the origin, right? The other will be time-likely related or space-likely related to it, right? So this is my x, this is my y or y prime. It depends on the time-like. This essentially means whenever they are space-like, this kind of space-like. If they are space-like, the commutators will always give 0 result. In these 2 operators are commute. This expands the meaning of the sentence. Commute means what? Commute means these 2 measurements. This measurement is a little not so precise, but essentially means the measurement here essentially means that you act an operator on this. Okay? Act an operator. So we know all the physical observables related to quantum mechanics related to operators, formation operators, real operators. Okay? So acting by this operator roughly explained by a measurement. So if these 2 operators essentially compute, you can see this measurement and that measurement has nothing to do with it. They don't affect. Then there is no causal relation. Yeah, this is a more careful or precise way to clarify the causality, and we can see that the commutator is a good detector for the causality. Okay, so we've spent a few minutes to complete this causality discussion. Let's go back again to this propagators. So another way, property, this propagator to simplify one should check is how this, what happens if I try to X this box plus m squared on these propagators. Okay, for instance, 4 different kinds. What do I get? Or another motivation or another question we should ask is how these propagators, we're talking about so many, right, different kinds, how these propagators are related to Green's function. You know very well about Green's function, right? From your second year undergraduate course. Everybody knows Green's function, right? Right? Green's function is a approach to solve the system, right? Right? You still remember what is Green's function? So how to define the Green's function? How to define the Green's function? Sorry? Yeah, that's one piece, but the more elementary definition, fundamental definition for Green's function is what? Depending on the delta source, right? Remember that? That's the first step, okay? In order to solve the so complicated system, for instance, in my system, the source looks like a very generic shape, different distributions. It's okay, I can try to use the Green's function approach. The Green's function was defined by, I first only look at the solution corresponding to a delta function source, okay? On the right-hand side of my differential equation, you see? I try to find the solution and then eventually combine these guys into my final solution. This is called a Green's function. So, as you might observe, some of the properties of this propagator looks a bit like a Green's function. So, how to clarify the precise solution? So this is equivalent to ask. So the next thing we want to discuss is the Green's function. This is equivalent to ask, what if you put a operator box plus m squared? Try to check if you act this operator just directly to the propagator, what happens? For instance, dr. I choose the particular which is the retarded one. Okay. We know how to define this dr. Okay. Now I try to act by this operator. What do you get? The same question. So let's do this calculation. It's either important. You still remember the definition of dr? dr is defined using a single theta function, right? Remember that? What's the definition of dr? So let's work it out. Since dr is defined by a theta function times a commutator, right? Remember that? Now, by acting this kind of operator, you have to take care how this differential operator act individually on the theta function piece and also on the commutator piece, right? Now, basically, you get the you just plug in the definition of dr and just try to act by this operator, and this will be the result. After a few minutes calculation, this will be the result. Okay? Because this is the second order derivative, you see? It's a second order derivative, just add particular derivatives. You get these three terms. You get these three terms, okay? This is the second derivative acting on the theta function. This is the each is one's derivative. You see, the mixed term, which has the factor 2. See, and this is the last one, right? This is the second order derivative acting on the second piece, which is the commutative. Okay. Now, again, you can continue to work it out by realizing that even though this is a second derivative acting on the theta function, up to a total derivative, okay, up to a total derivative, this will be equal up to a total derivative. This will be equal to one's derivative acting on theta and one's derivative acting on this one, right? Right. This is a trick. We're using this trick when we derive the equation motion. Okay. We always use that trick. If the two terms equal up to total derivative, because we ignore the boundary conditions, okay, boundary terms, we think it will be. In that way, we can translate some of the derivative of some term to the other. Okay. Now, by knowing that, but of course you have to take care of the sign, right? You always, if you switch in this way, you have to compensate by minus sign. So then, once derivative of theta function, you get a third function. Okay. Once derivative, remember this is time derivative. Okay. In the box, there is both x, y, z derivative and t derivative, right? But since this one is only about time, you see, so only the t derivative, time derivative is non-trivial. Okay, that's the point. You see, here, you see. Now, the time derivative, as said, if we transform into the second piece for the first term, it will become a conjugate pi, right? Then it becomes pi x phi y commutative vacuum. This is the result for the first term. I worked it out. This is the result. Now, what about the second? Secondly, it will be plus 2 times the third function. Again, pi x commute with phi y. Okay, this is the second one. See, that's similar. See, that's similar. The sign is different. One is minus, another plus 2. You see? Now, fortunately, here you get nothing but a commutator of the conjugate momentum and phi. You see? And times the delta function. Delta function means what? Delta function means this time should be equal. Otherwise, it's 0. Okay? So the delta function constraint, the time should be equal. Then this is nothing but the equal time commutator between pi and phi, which is precisely the quantization condition. You can use quantization condition here. Two terms are the same now, up to the coefficient. So this is the third term. The third term is 0. Why the third term is 0? The third term is this one. Did you see why the third term is 0? Yes. Why? Why the third term is 0? That's right. We use equation of motion. Okay. This notation a little bit abstract, but you should always keep in mind. Whenever I act on some operator, like sandbox operator onto this one, actually means this operator is the local derivative only associated for act on x. Okay? See, this is about the derivative of x. And then here is the derivative associated with x. Then you can see, I can see if you plug in this differential operator inside onto this file. Right? With all the other structure you can pass through. Okay? Because this differential operator is not a quantum operator. You can just say it's only x on x, that's the point. Okay? So you can just drag it inside upon this file. By using equation of motion, it must be 0. because that's equation motion. Then we get the result of these three terms. Then as said, you take use of the quantization condition, then eventually you get minus I delta function. Right? Because the equal time quantization condition gives me a three-dimensional delta function, okay? Times with a delta function for the time direction, which is delta x0 minus y0. Together, I get a four-dimensional delta function. Okay? So this is the final result. Now this means what? This basically answers the question I have asked you, right? Look at this left and right. What does this mean? This means dr is a grid function, right? It's the definition for grid function. It's learned and you can figure out very close again. Now this is the differential operator acts on object. You get the delta function, okay? This is the definition of grid function. This essentially means drx minus y. It's really the grid function. It's really the grid function. Okay. Now here I explicitly checked one of them, but you can check. This means that dr is grid function. But you can also check the others. For example, for df, you can actually check for all these four different types. They are all grid functions. Okay? This is also equal to minus I. For instance, you can also check for df. For df. I checked for dr. You can also check df. You can also check for other dA, df, tutor. They are all grid functions. By doing the same calculation, check it straightforward. This is the relation between this kind of property and this one, right? Now to test how much you understood, let me ask you a following question. Then what about the initial simplest Weidmann function? Is Weidmann function a good function? Yes. No? How many of you know? Is Weidmann function a good function? What do you think? Any answer? Okay, there is a yes answer. What about others? No? Right? The answer is correct, but the reason is confusing. What about the others? This is the same question as by asking, what if you act such an operator on the Weidmann function, right? What do you get? What do you get? Any answer? You get 0, right? Why 0? That's right. Just simply, I already used this fact in this step. Okay, step. So I hand you a Weidmann function, which Weidmann function does not include any step. Okay, just simply two insertions. Okay. Now your operator is only about to take derivative at x. You can drag it inside. Then you see by equation of motion, this is 0. Okay. This is 0. So where is my Weidmann function? Anyway, just a comment. So when the function is not. Yeah, maybe we should have a break. Yeah, let's have a break. 然后那个比例是把它放下去，只要所有的好，没有提质量都是没有在这个地方出个电。哦，老师，这个上课用的这个 annotation 都是遵循哪一本书？
没有哪一本书，这书现在都要矫正的。
那我现在参考的是这个啊，是说哪是这个改的。Right. Asking you the best. 有一小段，基本上。就是这个往上一个是不是抄错了？
还有个好处，就是你可以认为这个被记录东西是个 momentum space property， 是做四维变化，所以你可以认为这是 momentum space space property。有的。你讲我们 space 分明白我就讲。
老师啊，所以我们出来是为什么又有论文是为什么不要求一种性？
啊，为什么这样？那你这样不就感觉时间跟空间？它不是一家吗？原来一来就不等价钱。对，但是你看，他论文啊，他论文这个就有的时候，在场面里面说就是没有，谈的一些结构，但是 again 还要
Okay, let's continue. So basically finished all the discussion about the propagators. We clarified the relation between propagators and Lagrange function. And up to now, everything about the free theory. So the next question will be, what happened if the theories have some interaction? If we want to study interacting theory. That will be the next question. And, so what do we mean by interacting theory? That's the first elementary thing we should clarify, right? What do we mean by the interacting theory? So up to now, we only deal with something like equation motion. In terms of equation motion, we only about something like this. So if you look at such kind of equation motion, it only include the linear part. Linear means what? Linear means proportional to time. Okay, proportional to the field. That means linear, right? Okay, linear says combined, linear combined, right? When you want to go to non-linear, you want to have some terms, in the equation motion level, you want to include terms. like I square or I cubic or I quadratic terms. This means nonlinear, okay? Or means interaction, okay? So by interaction, it really means at the equation motion level, we will have terms go beyond. We will have terms go beyond this only linear I terms. If you have such kind of equation motion, then it means you have interaction. For example, terms like square, cubic. Okay. Now this is only at the level of equation motion. Now go back to the Lagrange. Okay. This is essentially meaningless because we know equation motion is from the variation of the relative with respect to I for the Lagrange. The lowest one's order, right? Now, the level of Lagrange interacting theory essentially means that the Lagrange will only include the quadratic, which is phi squared, or partial phi squared. Well, only those terms are also include the higher terms, phi cubed, false. For example, typical interaction will be the phi to the fourth term. Sometimes we call this is lambda phi fourth series. If you add such kind of term into your free series Lagrange, you add this term. For instance, if your previous free series Lagrange is L0, then add up this additional term, then the series becomes interactive series. Like that, because that kind of term essentially calls the nonlinear terms in the equation motion. You can derive the equation motion out of such kind of Lagrange. Okay? You get a nonlinear terms in your equation motion, which makes the series, interactive. Okay. Now, what is the physical way to deal with the interactive series? Now, if you are a naive person, you may just try to follow what we did for free series, right? Remember, when we want to quantize a free series, we just make an analog to the harmonic oscillators. Now, maybe someone is very naive. They try to claim in the following way: why don't you just perform this, 5 steps we listed before for the interacting series, right? You can do that in principle, right? Then you try to follow the step 1, 2, 3, blah, blah, blah. Then you immediately meet a problem, okay? You can't basically find a concrete solution for your equation motion, basically for any interacting theory. There's no exact solution for interacting theory you can find. In free case, you can easily get it, right? Right? You just do the something similar to cosine sine condition in this more 4-dimensional space. Do this p-space decomposition, okay? Decompose to all these p modes, be combined together, integrated together. Then it gives me a solution for free series. But if you do the same thing, you want to try to find the similar solution, exact solution for interacting series is impossible. That's the main difficulty. We cannot do it that way. So that's step 1 to 5 doesn't work. That's the one difficulty. Because the dimension. Now what? Now, yeah. So we basically choose like we don't think that this is this problem is so simple. For the we try to my what do we do? We choose a more physical, before solving this theory, we choose a more physical viewpoint. And try to relate the interacting theory to fragment. Okay? So we need a sharp motivation. Which kind of problem we can solve? Or we could have solved for the interacting theory. As mentioned before, we have many different formulations in this course, but all of them is prepared for a very complicated problem. Now here is the example. We try to ask a very, very complicated question for the interacting theory, and then we try to solve the problem. So what is that? So the way is to try to relate it to experiment. Which kind of experiment? So that's the Reynolds experiment is example in quantum physics. This experiment called Propagators. This essentially means that in order to try to eventually understand the interacting theory, we try to set up the problem in a concrete way. We try to ask from the experimental point of view, if the physical system or the physical process is fundamentally related to an interaction theory, what we can observe? So this is related to the famous physical process. In other physics, we do nothing about scattering, right? All this, this big term, HC. It's all about just kind of scattering. So how to define the big problem? It's set up in a constant way. The way to do it is scattering means just that if I take some initial state. Let's say I can take a simple. We learned in the last week's course how to give a definition for free particle state. Remember that free particle state can be obtained from free theory. So that, for instance, we can have some state like this, right? I'm getting familiar with that, right? Last week's. Now we take use of that. We try to prepare some initial state precisely as such kind of state, momentum eigenstate. And then we try to evolve them. If the theory is interacting, it just means the particle will interact continually. In free theory, they all pass through, they don't touch. But in interacting theory, they just very we think in some time regime, final time regime, we will sufficiently evolve or interact with each other, and then outcome will also become some free particles. Some functions like this. This is a very basic picture. I draw this picture essentially that same time evolution direction. I evolve. My time direction is from right to left. Okay? Then this picture essentially means at t equals to minus infinity, I take two particles. Okay, they are very far away from each other, right? Right. Now I design the momentum of these two particles. Let them try to collide, right? Now they try to collide.
Now, in the finite time regimes, because the series is interacting, they will just scatter, interact with each other. Okay, right? And this is the LHC experiment. And then, after some time, okay, after some time, the final state will be again because they collide, right? Collide, they're scattering. There's outcome particles again, right? Then I just wait. I wait a long time. Okay, wait a long enough time. You will see that the outcome will become again some free particles far away from each other, right? This is the collider process, right? So it's very intuitive, right? This picture. So by this time domain, I mean the interaction regime. Yeah, this is the time direction. So this is the setup to try to absorb something heavily related to the interaction. Okay. By the way, this process is trivial if the series is free. That's why we designed this setup prepared for understanding the interacting series. You can imagine that, right? If the series is free, what will happen? What is the income and then what is the outcome, right? Because everything is passed through each other. Okay? If your initial state is something like this, okay, we have one more. If this is your initial state, since the series is free, eventually the state does not change. Okay? Final state is do it again. Free series don't have any everything passes through. It's always a momentum identity. Okay. So that's so this has how we become trigger. But it's not trigger for interactive series. That's why this stuff is pretty useful to understand the interactive series. Okay. So let me, since this is the important step to understand the symmetry, to understand the interactive theory, it makes sense here. Yeah, at t equals to plus minus infinity, one can ignore the interaction. Therefore, the in state and the out state can be described by free particle state. Yeah, this free particle state, we also call them a particle state. As said, for instance, you can specify your in state. I put an I here, I means in. I means in. Your in state could be, let's say, 2. Here, 2, P1, P2. 2 particle states. Okay? And then 2 particles. Now, your outcome, your final state. F means final. Is again the free particle state and the current state. Okay. Now then you ask the question, so what happened for the intermediate? Right? Which kind of mathematical tool or correct proper setup can represent, describe this kind of interaction or evolution process in this interaction handle bank. As always, we just in QFT have to use a tool of operators. Treat almost everything as operators. Then we should build up some just using operators to describe. Okay, that's the idea. It's also perfectly consistent with what we learned in quantum mechanics, right? Quantum mechanics, again, in Heisenberg picture, okay? Heisenberg picture, we include the time evolution inside the operators. Okay? Operators are time dependent. So in Heisenberg picture, basically the evolution process is simply described by a operator. So you can try to formulate it. For example, we can consider the evolution operator in this way. Okay? Some evolution operator, for instance, U operator. As I said, in Heisenberg picture, the operator can have time dependence. The operator is evolved from t equals to minus infinity to plus infinity. Okay? Let me, at this moment, just put an abstract U operator. Take the duty of do it. Now, it basically evolved from an initial state, okay? Initial state through this evolution operator, and then eventually overlap with the final state. This is the whole amplitude, similar to quantum mechanics, right? Let me be more precise. This is the Heisenberg picture, H. We also understood in Schrödinger picture, the time evolution is encoded in state, right? If you want to switch to the Schrödinger picture, all the time evolution is included already in the state. So it's a simple overlap using this state. This is the Schrödinger picture. But we frequently use this one, okay? Not this one. Just to clarify. If you want to insist, I do like the Schrödinger picture, then right inside is what you have to do. What you have to do. It's a little bit abstract, and this kind of setup is really particular. So to make everything very precise, you have to put more effort. For instance, this kind of abstract state essentially means, in quantum mechanics, we know how to evolve a Schrödinger state, right? Right? For example, we can write down the evolution e to the minus iht, okay? To evolve the state, right? Then we get another state at another time, right? Remember that? The unitary operator to evolve the state. Yeah. So to really calculate this overlap, this one and this one, because they are located at different time, you see? Yeah. First thing you have to evolve, then finally take the overlap. So you should try to evolve those states in order to calculate this overlap. Anyway, we want to focus on the first picture, but always in QFT. In Heisenberg picture, it's more simple. We can just abstractly take this. There is an evolution operator, it's characterized by U, okay? It evolved from time t equals to minus infinity to plus infinity, and the in state is a simple free particle state, the final state is again a simple free particle state, okay? Then you can just try to define what you want. Indeed, we defined something called the S matrix in this way. The U operator is, of course, in general, very complicated. But no matter how complicated it is, if you know it, okay, if it's well defined, I can take use of this definition as my so-called S matrix. S matrix is defined in this way. Now, I set this subscript index F and I corresponding to this final state and initial state. Okay, from left to right, from I state to F state. Okay? This means what? This means take S matrix as a matrix. All these different I and different F becomes index. Okay? It's a big matrix. You see? We learned in last week that in Fock space, it depends on how many particle number you choose. I can have many different free particle states, right? Eventually means that you can have many elements for this S matrix. See? Many different elements for this S matrix. Okay. For instance, I can choose a two particle in, come in, right? I can choose a 3 out. I can also choose some other 3 in, 5 out, like that. All these corresponding to different elements of this S matrix. Okay? Clear? Now go back to the free. You should always check back to free series. What happens for free series if I look into the S matrix? Any idea? That's right. It's a direct function. It's a direct function in the IF index, right? It's a direct function. So in the free series, it's a direct function. Right? Direct function, as a matrix is equal to identity matrix, right? I write it the matrix in the different I labeled, F labeled space is an identity matrix. This essentially means the trivial part becomes of this entire S becomes an identity. Then we can isolate the non-trivial part by minus this identity, right? For example, I can define the S equals to some identity plus some IT. So from this S, I'll view everything in terms of metrics. Okay? Like that. In terms of metrics. I can decompose the isolated identity from this entire S matrix. Then I can define a T matrix. T matrix is sometimes called the transfer matrix. Never mind. This is T. And this kind of definition, as you can observe, because this T is sensitive to the interaction, capture the interaction. So this is useful. Right? T captures the interaction. So in the free series, T is 0. So T is sensitive to whether your series interacts with 0 or not. Now you can go further. Because of in all this scattering process, the total momentum is observed. The total momentum I actually all momentum, including energy, right? That essentially means what? That essentially means there's no external force, or there's no external source for this process. Process is entirely involved by themselves. Okay? How much you have initial particles just scattered by themselves, and then eventually come out. You don't disturb it in this scattering process. That's either some external way. You don't do that. But that will break conservation of energy. If everything is by itself, you work by themselves, of course, energy needs energy should be always conserved. So there is a conservation. Therefore, we can continuously try to define something more concrete by isolating this conservation. See, I can define the T, I can isolate some factors out of this T. See, I can have the force. This third function essentially captures the conservation. Then I can get some metrics like M metrics. See? So 2 pi is already here, some of my big factor. Okay? See? I can isolate the third function because of physical conservations here. Okay? Now I really get something M. This M looks like depends on the interaction of that theory. Okay? Interaction of that theory. usually depend on the interaction. So this M is usually called the scattering average. Yeah, all this is about some definitions about this particular setup, scatter setup, and scatter some incoming particles, and then observe what are the outcomes. A few remarks. As mentioned, since the U matrix is the evolution operator. U operator is the evolution operator. And S is entirely defined coming from this U. You see, S is the matrix element of U. Okay. So in this case, this S matrix is integer. Because the time involved looking operator. S library. The S matrix. The second remark is the emphasize both in and outer state are the free particle state. Here, by free particle state, we really mean the own shell. The physical state, not off shell, own shell. Right? The own shell state. Own shell means satisfied, own shell condition time. The state will be checked. History of Hassan Square. That's the condition. That's from the square. On the shell. Free from the shell. State. And this state is in a box space. Which I learned last year. So that's just a free particle state. We know how to create that kind of state. That's by using AP diagram, right? You can add many times. If you need many, then add many times. That's it. If you need many, 1, 2, you add it twice. AP1 dagger, AP2 dagger, acting on the ground state. That you will get. And for the F, is the same thing, right? So F, this one is just a conjugate of this one. You first create the F state and then conjugate to get this final step, right? Now, the only thing we don't know yet is the details of this evolution operator or this S-matrix. So why we just jump into this kind of new concept in order to understand the interacting theory? The reason is because this kind of looking very physical object called the S matrix is in fact directly related to the correlation functions defined in interacting theory. Okay, we were very familiar with the correlation functions. We'll just talk about many different propagators. These are all different kinds of 2-point functions. There's 2-point correlation functions. Okay, it's just different type. Okay, now. In principle, we should just continue in that way, right? Let's just compute the 2-point function for the interacting theory, right? That's more natural, reasonable way to push from free theory to interacting theory, right? But we switch a little bit to another physical motivation. Why we care about such kind of object? Or in another word, how the correlation function in interacting theory can be useful in the real experiment. Yeah, there is a very short way. This is directly related to the guy I defined here, the S matrix. S matrix is directly related to the correlation function in interacting. That's the claim. Yeah, this claim is so-called SE formula, state reduction formula. I'm not going to. These are 3 people. Zeeman, Zemanzik, and Zimmerman. Three people. So by this so-called LSD formula, we can directly relate it S matrix. S matrix. Say, if I write it this way, it automatically means I'm working on Heisenberg frequency. That's that before. Now, this is related to the correlation function. Say, this part you should be familiar with. Because this is nothing but the correlation function. Okay. What is omega? Omega is the vacuum state. But now I want to distinguish the vacuum state for interacting theory with that for free theory by using different labels. Okay. I use omega rather than the zero state. I use this one to denote the ground state for interacting theory, not free theory. Because now everything is in the interacting theory. I'm working on interacting theory, right? I have to compute all things in this for this new ground state. Now, what is this guy? This T is just introduced a few minutes ago. This is the time ordering operator. Okay. Whatever is included in this bracket, I let them. If you give me a particular insertion, I just let them time order. Okay. This T does. Okay. Time order. Time order means what? The earlier time, and said the earlier time is always on the right. Later time is always on the left. Insertion. Okay. You insert an operator in the space time. I do it that way. This is called the time order. Now, times some free factors, this will be equal to the S matrix. Okay? Now, in principle, we have to work out what are the free factors. But before that, you can guess a little bit. Following the definition of the left-hand side, we have something in mind. This left-hand side, because this I state and the F state is captured by the momentum eigenstate itself. Right? So the momentum, the incoming momentum and the outcome momentum to be parameters. So the left-hand side must be in a certain way to relate it to some momentum, okay? Given momentum. Right? But only this part is not enough, right? This is only about in your space-time, I inserted a bunch of local operators and take the correlation function, vacuum average, and time ordered, of course. Okay, that's the right-hand side. So this part has to do the job to transform from X space to some kind of P space, right? See, but this is essentially a P space object. Okay. I explained the S matrix is indexed by this incoming state and outcome state. And all the incoming state and outcome state is captured by the momentum eigenstate. Essentially means different P. Okay? So you can think about your S matrix actually defined in your P space, P eigenstate space. Just parameterized by different P. Right? So what is this guy? So this guy must be something looks like a Fourier transformation. Okay. See it? Indeed, it is, but I'm not going to prove it. You should do it. Let me write that. It looks a little bit of horror, but actually very simple. Yeah, this is this part. Let me explain a little bit. What is this? If you forget about this small bracket or this box 1 to the box n, then this is nothing but what? Fourier transformation, see? Right? Nothing but Fourier transformation, see? Now, above on this Fourier transformation, you insert a little bit more object. Looks like this. It's just a box. Okay? Box 1 means what? Here by P1 with a minus sign in this x column, I mean all the in-state parameter P, okay? You see, I put a minus P1, but eventually I have a plus Pn. Yeah, it means in-state you have minus sign, out-state you have plus sign. Okay? This is to define this formula. Okay? Making it very defined. Now all the other operators are just a similar structure, doesn't matter. So that's the same structure. And then you insert. Depends on how much incoming momentum and outcome momentum. You should insert how much factors here. This means dot, dot, dot. Okay. So if I have 1, 2, 1, 2, and 3 to n, then basically you have to put n different factors here. With only P1 and P2, the sign in front of P1 and P2 is minus. Okay. But all the other from P3 to Pn plus. Okay. Then you have the formula. Okay. So this is the concrete relation. You can see it similar to Fourier transformation. Relate this time ordered n-point correlation function to this S matrix. Yeah, that's the so-called ST formula. As said, the proof is not difficult, but it's just a little tedious. You write a formula again and again. Yeah, I encourage you to do it yourself. Yeah, it's not difficult at all. It's just remember that all the universal formulas cannot be too much difficult to prove this. Because it doesn't matter which theory you're talking about. It's always correct. Then it means you just capture some very, very elementary relations. Yeah, if you are somehow scared by these long formulas, I can provide you how to understand it. There is a quite a simple physics picture behind this formula. Okay. Okay. So what I mean is, if you draw this m-point function using a diagram, right? These are just the x1 to xn m-point function, right? I can say, okay, this is not about something. Yeah, I'm just trying to picturize this formula. This is nothing but some x1, x2, right? And dot some x3, xn. You have many n insertions, right? At each point, you have operator insertion at that point. Okay? And that is about a correlation function that I can schematically capture and right inside this picture. See it? Right? Now, to measure these correlation functions, you should try to use your propagator or interacting structure to fill up this diagram. Okay? For example, anyway, just a very schematic, you have to do something, some contractions for this complexity to fill this diagram to compute the right hand side. Okay? So this is what we call the m-point function. Actually, very soon, depending on how much time we have, we will see how to derive. We have 10 minutes. Maybe. Yeah, we can show how to derive this kind of diagram in a concrete way. Just a little bit explanation to this is the so-called m-point correlation function. Now, what happened for this one? As I said, this is about to treat this. These are just incoming. This is corresponding there are some corresponding incoming particle and outcome particles. Okay. Then this is the so-called S matrix. So this part, this additional insertion or Fourier transformation, essentially does the job to move this this kind of external legs. Because correlation function will include those legs, okay? But amplitude does not. So just throw away this kind of include by multiplying such kind of factor. Actually, in momentum space, this is nothing but the propagator, you see? You can switch to the momentum space, because the whole point is just to Fourier transform this object. Okay? I can just replace this box 1 by a P1 square, right? Right? P1 square. Now P1 square plus M square is nothing but the factor which can cancel this momentum space property, which is essentially those legs. Okay? But anyway, the simple picture behind this long formula or SD formula is I give you a correlation function. I want to rid of something else more related to this kind of experiment. What I should do is remove these legs or cancel those legs. Only maintain the structure inside. Okay. Anyway, that's the rough explanation. And I wish I could finish the Feynman discussion within 10 minutes. Is it impossible? Right? Yeah, it's impossible. But I can sketch the ideas and try to finish it next time. Yeah, the next, as you can see, the next thing we will do in a concrete way, just to compute this object. Okay. We're going to compute this one explicitly. Then eventually, we don't derive this factor at this moment, but eventually, when we know how to handle this, how to compute this object, eventually we will do in a very precise way how to reproduce this schematic as left-hand part. Okay, it's not a big deal. It's, you can say it's just a formula is known. So what do we do now? Same, we have to here ways is to calculate the correlation function in direction theory, right? So what is the simplest object of such kind of goal? First thing we try to compute the simplest one will be a two-point function, right? And we have ordering that deal with this x and x prime. The first exercise, the first goal is to handle how to do adjustment. Then you know how to do anything, right? Yeah. Now, x is the correlation function defined by the direction theory from the direction theory. The question is how to do this. How to do this. Looks a complicated task, right? But even before those touch factor matters, what we achieve before? What we achieved before is by doing the quantitation property of free series, we able to compute all the correlation in free series, right? Right? Because we can do that. Just try to find some of A and A baggers, try to use those different relations A and A baggers. That that's something we can handle. This seems a new problem. Even before solving this problem, you should go back to justify the key ingredient
we took to solve the detail problem. What is that? The only thing we couldn't derive from somewhere else is the quantization condition. Quantization condition is something we put here for free theory, right? We didn't claim we can derive it, we just input and check the results. Realize all the results make sense. Now, what happens for the quantization condition for the directed theory? That means the zeros order has to be lost, right? Yeah, let's go back a little bit to justify those conditions. So, for instance, in free theory says we impose the equal time commuters of phi, right? This is one of the several conditions to actually one of them. This is equal time commuters. Now, I'm asking whether this condition is true in the directed theory. What do you think? How many of you think that? The answer is yes, right? Right? Because we just some time ago we just justified or interpreted again this kind of relation in relation to authority. Authority model. So it's like a computer. So I understood such kind of relation deeply related to authority. In what? It doesn't matter what you raise theory, direct theory. We don't want to violate authority. We provide the fundamental principle. Right? So we should insist such kind of condition. It's still a good justification. So this is a what happened for the other one? What do you think about it? This is the phi commuter, right? Now write phi as the height of T5. Write phi as the height of T5, and this is the other one. What do you think about this condition in the direct theory? Is it true or is it violent? What do you think? It seems a bit harder to answer this question. There's no immediate argument to justify whether it's still true. But in fact, it's still true. So what is the argument? The argument is this. The other relation, I said this is kind of deeply related to what is. This is a deep what locality. Locality, not really. No, not really. So in fact, this relation is deeply related to the uncertainty function. Okay? We don't want to change the uncertainty principle. Depending on whether the series is real. Uncertainty principle is again fundamental principle. And quantum field theory is only about the magnitude of system. Even the magnitude of system. We don't want to value that. But we know very well XP configuration quantum field immediately gives the uncertainty principle. Okay. So we think this again is still true. So these are the, of course, there are a few others. Yeah, this is just the main claim is the commutation relation or quantization condition is still true in interacting theory. Okay, then we can try to use some techniques to work out. That's the job. Next lecture. Let's stop.